right, hello. So we are going to do the next chapter, and we're going to be covering 2.10 to 2.12 and continuing the conversation of acids and bases. So let us pray. Dear Heavenly Father, Lord, thank you so much for today. Please be with us as we cover this content. Allow them to understand the significance of acids and bases in reference to organic chemistry. All right, so let's first talk about organic acids and organic bases. All right, so organic acids are characterized by the presence of a positive polarized hydrogen atom, okay? If we have a positively polarized hydrogen atom, so for that to occur, let me get my pen. Let's look at it here. This oxygen is electronegative. Remember we talked about in the other chapter, we talked about dipole moments, okay? So this is a polar covalent bond. Because this is polarized, it is going to be slightly acidic, all right? But notice it's only a little polarized, and so the acidity is not going to be as strong as when you have delocalization. So now here is, let's see if I can undo that. So here you have, let's see, get rid of that. Here you have the polarization, because of delocalization, is going to be even stronger, okay? Apologize, my pencil is not wanting to cooperate, but that's okay. Let's see if I can do it again. Okay, so notice the proton here, because of the delocalization, is even more readily to be given up. And so the pKa is going to be higher. Now we're looking at acetone. There is a little bit of polarization. Now this is a, what do you want to call it? This right here is not a polar covalent bond as much as the other ones. However, it is still, it's not very acidic. However, you do have some bit of acidity in it because of the oxygen here does create some polarization, okay? And you can see that here. So it does have some polarization. All right, so two main kinds are those that contain hydrogen atom bonded to an electronegative oxygen atom. All right, so if you have OH, we know that that is going to be an acid. And a hydrogen atom bonded to a carbon atom next to a carbonyl group, okay? So if you're next to a carbonyl group, that anion is stabilized by having a negative charge on a highly electronegative atom. So let's look at it here. So when this proton leaves, because this right here is going to create a negative charge, because oxygen is very electronegative, it's okay and it will stabilize it. Also, if the hydrogen leaves, not only is this oxygen stable, but because of delocalization of this, it stabilizes it even more. And so this is the one that was it was the most acidic. So whenever you have delocalization, we know that that's a very strong acid. Here, you'll notice that when the hydrogen leaves, you have this anion here. And again, because of delocalization, with that, you're able to still get that stable anion. Now, again, acid strength. This has the best delocalization. This is also acidic because it's directly creating an anion on the oxygen. This is acidic because of the delocalization. Or not delocalization, but because of the transfer of protons. Well, it is still delocalization, but it's not as stable because the carbon has to hold a negative charge, and it's not as electronegative as an oxygen relative to this one right here. And so because it's not as strong, it's not as electronegative, this delocalization isn't as stable as this delocalization, okay? And it's going to actually favor this species more than this species because of the electronegativity of that oxygen. All right, so organic bases. Organic bases have an atom with a lone pair of electrons that can be bonded to a proton. So nitrogen-containing compounds derived from ammonia are the most common organic bases. So when you have an ammonia, NH right here, this is called an amine. All right, an amine. So when you have an amine group, which is an NH2 that's bonded to a carbon, these electrons here are going to be basic. This is the most common base that you see in organic chemistry because these electrons are very readily available to pick up a proton. Kind of similar to how ammonia is a very strong base. All right, so oxygen-containing compounds can react as bases as well when the strength of the acid or the acid with a very strong base, okay? So, for example, you see you have an oxygen here. You have these lone pairs that are also very, are available to pick up a proton, okay? So they are available to pick up a proton. Same thing with these electrons. They're available to pick up a proton. So they can act as a base. But again, they're not as strong of a base as the amine. All right, so this goes into our next definition of acids and bases. I know last class we talked about the definition of acids and bases in reference to the Bronston-Lowry acids and bases. So now we're going to talk about Lewis acids and bases. And now listen, these are just different definitions. A Bronston-Lowry base and a Lewis base, or Bronston-Lowry acid and Lewis acid, are just the way that we relate to them. They don't have to be one or the other all the time. They could be both, but it's just what you're looking at. So a Lewis acid is electron pair acceptor. So if you look here, this orbital is free and available, okay? Because this orbital is free and available, it can accept protons to be moved into it. A Bronston base has a pair of donors. And so here, this orbital is full. And so this base can react and overlap orbitals with this acid, creating a bond here. So the base can overlap with the acid, creating a bond. All right, so Lewis' definition of acidity includes metal cations such as magnesium. Okay, and so this is a broader explanation of an acid or a base because we're looking at compounds that don't have protons available. So we often use the Lewis acid and Lewis base definition when we're dealing with things that do not have protons. So we look at this and we notice that the magnesium is positively charged, therefore it has empty orbitals available. Whereas the oxygen here is negatively charged, so it has additional electrons in its orbitals. So this would be the acid, and this would be the base. So again, the one that has the empty orbitals is the acid, the one that has the filled orbitals is the base. So group 3A elements such as BF3, AlCl3, sodium chloride, boron fluoride are all Lewis acids. They have unfilled valence orbitals and can be accepted electron pairs from Lewis bases. Okay? And so those, whenever you see those, you know those are Lewis bases. So transition metal compounds such as titanium chloride, iron chloride, zinc chloride, tin chloride are Lewis acids. That's because they have electrons, they have empty orbitals that can be, the electrons can fill them. So let's look at some reactions, okay? Well, let me go back, actually. I might have went too fast. So you guys can make note of that. Okay, if you need to pause it, go ahead and pause it. All right, so if you look here, you'll see boron trifluoride is going to act as your Lewis acid. Here, you have your oxygen that has these extra electrons. And so the electrons here are not actual extra electrons, but it does have orbitals that are filled with electrons. They're going to attack the boron and create this acid-base complex. Okay, the acid-base complex. And then here, this oxygen here is going to have a positive formal charge because oxygen has valence electrons of 6, and then you have 1, 2, 3, 4, 5. So 6 minus 5 gives you plus 1. And so you see that positive formal charge. And the charge is conserved because this was neutral on this side, and these two anions cancel each other out. So this is also overall neutral. All right, so Lewis bases are compounds with a pair of non-bonding electrons that it can use to bond with a Lewis acid. So this is, again, we just talked about that. So you have a pair of non-bonding electrons. So you have lone pair electrons that can be used to bond to a Lewis acid, which is the orbital that is available. Now, these can accept protons as well as Lewis acids, okay? So remember that these Lewis bases can also accept protons. This definition encompasses that of the Bronsted bases. Oxygen and nitrogen containing organic compounds are Lewis bases. They have lone pairs of electrons. So we have a compound that includes oxygen or nitrogen. These have lone pairs, so they can be Lewis bases. Some compounds can act as both acids and bases. So it's important that when you look at a compound, some of them can act as acids and bases. It's just based on what they are in the presence of. And you see that with water. All right, so here's some common Lewis bases in organic chemistry. And so remember we talked about how alcohols were also acids. Well, in this case, they can also be a base because you have these electrons. So notice every single last one of these all have electrons that are lone pairs. Pause it if you need to. I'm about to continue on now. All right, so let's do an example. So we're going to use curved arrows, called a mechanism, okay, to show how acetanilide can react with a Lewis base. All right, so a Lewis base donates an electron pair to a Lewis acid. All right, so if we're looking here, a Lewis base here donates protons to a Lewis acid. So this, donates electron pairs to a Lewis acid. So these here are coming and donating it to this hydrogen. When that happens, this bond breaks and pushes these electrons here onto the conjugate base here. So you see these electrons here? Those extra ones came from this bond here. All right, we're going to be doing a whole lot more of these in organic chemistry. But notice, I just want to point out, with these arrows, they always start with the base because they're showing that these electrons are coming in and grabbing that hydrogen. So it's kind of like electrons are arms. So the electrons on the oxygen are coming and grabbing the proton and taking it away. And initially, this part of the molecule here, this right here was its arm. So this arm was holding on to this hydrogen. When these electrons came and grabbed the hydrogen, because hydrogen can only hold up to 2 electrons, this one had to let go. So I like to think of it as a relationship. So the oxygen is just like, hey, hydrogen, come on over here. And so as hydrogen is getting picked up and being taken, hydrogen is letting go of the original person. And because of that, now the original person is available to mix and mingle. All right. So the acetanilide stole hydrogen from whoever this was. And this could be any compound that is acidic. Okay. And now the new conjugate base, again, is ready to mix and mingle. And they're just a happy pair. Oh, one more thing to point out, the charge is conserved. So as it did move, notice this was neutral. And so you always have to check your formal charge. Always check your formal charge. You always have to show it. You always have to show it. And so when this lost it and these electrons went here, something has to be positive in there, okay? And so that is the oxygen. So whenever you're doing reactions, after you're done pushing your electrons, check your formal charge and show them. They must be shown. I can't point that out more than enough. All right, so what about non-covalent interactions between molecules? All right, so this is one of a variety of non-bonding interactions between molecules. All right, so some non-covalent interactions are dipole-dipole forces, dispersion forces, and hydrogen bonds. Okay? So let's first talk about dipole-dipole forces. So dipole-dipole forces occur between polar molecules as a result of the electrostatic interactions among the dipoles. So depending on the orientation of the molecules, the forces can be either attractive or repulsive. And so if they are organized neatly, they can be attractive, which you see here. So like the negative and the positive, and then they're lined up. So this negative is next to the positive and so forth. And then this negative is attracted to these two positives here, lining them up nicely. And then this is on this side. And then as you can see that. So you see all the negatives are next to some type of positive and so forth. Or they could be repulsive. And so here, it's interacting with it, but it's not really lining up the same way. And then you have these here, which aren't going to line up because they're all negative, so they're going to repulse it away, repulsing them away. So notice that the like signs are next to each other, and so they're repelling each other. All right, what about dispersion forces? So this occurs between all neighboring molecules. This arises due to the constant change in electron distribution within a molecule. So if you have a molecule, and of course the electron distribution changes, so that's delocalization, and so it doesn't necessarily stay the same. It's constantly changing and kind of being spread out. And so because of that, the molecules next to each other are going to be there's going to be a force that occurs between that. You see this with hydrocarbons when you have carbon-hydrogen interactions occurring. All right, hydrogen bondings here is when you have compounds that have oxygens and nitrogens in them. Okay, so oxygen and nitrogens are electronegative, and so they like to pair up with protons in neighboring compounds. And so here you have your two water molecules, and you have this hydrogen bond that is forming between the two different molecules here, okay? Because of the electrons that are electronegative. And so you create these weak hydrogen bonds, okay? You see that also again with nitrogen, these weak hydrogen bonds. And so it kind of causes them to orientate themselves around each other accordingly. All right, so an example of this in biology is deoxyribonucleic acid segments. And so with those segments, you actually have hydrogen bonds between the DNA strands. And so you have that DNA that are interacting with each other because of the hydrogen bonding that's occurring. And so when you are separating the deoxyribonucleic acid into the two different strands, when it's about to do this replication, you need that hydrogen bonds to be broken using an enzyme. All right, so here's a work example. This is actually where we're going to be ending our lecture. Is of the two, vitamin A and C, one is hydrophilic and water soluble, and the other one is hydrophobic and fat soluble. Which is it? So can you guys look at the compound and realize which one is hydrophobic and which one is hydrophilic? All right, and remember we talked about before that like likes like. And so if something likes water, it's going to have something in it. And the one that does not like water is going to have something in it. So if you notice, vitamin C has oxygens throughout it, okay? And it's going to be polar, okay? Because you have these oxygens, hydrogens, oxygens. These are all polar things that can have hydrogen bonding. Compared to here, you have this large area of nonpolar bonds, okay? Because remember, carbon, hydrogen, they're considered nonpolar covalent bonds. Now you have a little bit here, but it's not enough. This compared to this is definitely more nonpolar. And so since this is more nonpolar, that one is going to be hydrophobic, okay? There's only one OH group. So this is not like water. This would be hydrophobic, whereas this one has several OH groups. Therefore, it's polar. Therefore, this is hydrophilic. Okay? And that is that. So when you're looking at solubility, you're going to be looking at which compound is more polar. And so you're going to have more OH groups or polar areas such as anions or cations present in the molecule compared to having mostly carbon and hydrogens in the molecule. All right, so here goes a summary of chapter 2. All right, so subsubstances must be shown as a resonance hybrid of two or more resonance forms that differ by the location of electrons. And so this was talking about the resonance. Remember, we talked about the resonance and hybridization, okay? And so don't forget resonance structures. Now listen, resonance structures are so important. You need to practice those. So we're going to look at some practice on the resonance structures. 2, a Bronson-Lowry acid donates a proton, okay? So Bronson-Lowry acids donate protons. Bronson-Lowry bases accept protons. Now, the strength of the Bronson acid is related to the negative log of the acidity constant. So that's the pKa, right? The strength. And so remember, we know that weak acids have high pKas and strong acids have low pKas. Now, a Lewis acid has an empty orbital that can accept an electron pair, and Lewis bases have an orbital or have extra electrons that can be donated in the presence of unshared electrons where you have those lone pairs. And last but not least, non-covalent interactions have several types: dipole-dipole, dispersion, and hydrogen bond forces. And so that is all of chapter 2. Next time, we will be talking about chapter 3 when we're talking about organic chemistry and its functional groups.